It was a huge honor and surprise to be selected by the Geo-Institute to give the Terzaghi Lecture. It did come with a lot of work and self-expectation. My whole professional career has been in the same building where Terzaghi started soil mechanics in the US almost 100 years ago. That's what you're seeing over my right shoulder. I also found out that I was the 15th Terzaghi lecturer with links to MIT. So no pressure. And since the lecture itself, I've spent much of last year fulfilling my promise to prepare a written paper based on the lecture. And despite my trepidation, this also turned out to be a really great opportunity. And, it was an opportunity for reflection and synthesis of my own work. So I really enjoyed that.
Terzaghi, I remember differently now for a little bit different reason. When I was notified, I was obviously just thrilled to death. And again, very, very gratified and thankful and wondering how I was selected. But looking back, the thing I remember is for over a year, I worked many, if not most weekends to prepare my lecture and then prepare the paper. It was both a labor of love and a labor that never ended. And, I don't know if I'm slow or it took me a long time to digest all the information and figure out exactly what I wanted to convey, but it went on and on. My wife, Anna, still makes fun of me for that damn Terzaghi lecture, as she says.
Brad, thank you for asking me to make a few comments in anticipation of today's Terzaghi lecture and to congratulate our speaker, Dr. Springman, for an eminent career, both in geotechnical engineering and in academe, and someone who truly is deserving of this honor. Being asked to deliver the Terzaghi Lecture, of course, is a great distinction for anyone in our field, and I was very pleased to have that honor a few years ago. Unfortunately, it was an honor in the middle of COVID, and the only time in the past and now that we've given the Terzaghi Lecture online, but hopefully we're through that period. This is an opportunity for anyone to give forward to the field, to share experiences, to contribute to the ongoing development of geotechnical engineering. So I warmly congratulate Dr. Springman. I wish her great success in the lecture, not that she needs those wishes, and congratulations.
I recall that as I was listening, or perhaps not listening, to the introduction, I was thinking really two things. I was feeling both apprehensive and humbled. Apprehensive because I know how many things can go wrong in a 50-minute lecture. Humbled as I thought of the outstanding individuals and their lectures that had gone before me, and of the giant footprints I was following. But all those thoughts disappeared the moment I opened my mouth to say the first few words. And for the next 50 minutes, I just focused on telling my story. With the applause then subsequently, I felt relief and honored. Relief that all had gone well, as I'm sure it will for you, Sarah. Honored to now be a past Karl Terzaghi lecturer. Congratulations, Sarah, on being selected as this year's Karl Terzaghi lecturer, and I very much look forward to your lecture.
Now it's time for Sarah. I've known Sarah for many years, and in this very small world, find out she's now working directly across the street from my former high school. So anyway, congratulations, Sarah, on being the 61st Terzaghi lecturer. I'm really looking forward to seeing you and hearing your lecture in Louisville. Thanks.
Hi, everyone. My name is Ellen Rathje, and I have the distinct honor to introduce Professor Sarah Springman from the University of Oxford as the 2025 Terzaghi Lecturer. Sarah is currently the principal at St. Hilda's College at Oxford, apparently across the street in Cambridge, and also emeritus professor and rector at ETH Zurich. She's a fellow of the Royal Academy of Engineering in the UK, also a member of the Swiss Academy of Engineering Sciences. And unique to our community, I think, she is also a Dame Commander of the Order of the British Empire. And if you're not sure what that means she's the female equivalent of a knight. Her research accomplishments span so many topics, including the application of centrifuge modeling to geotechnics, field tests to investigate mechanisms of mass movement for rainfall-induced landslides, and the response of post-glacial lacustrine clays. In so many ways, Sarah is impressive, but in this introduction, I really want to focus on the tenacity, leadership, and technical excellence she has exhibited over her career. Sarah received her bachelor's in engineering from Cambridge in 1978, after which she went out into consulting and worked on projects around the world, including Manasavu Dam in Fiji. But after learning that she was being paid less than her male counterparts, she went back to get her MPhil and PhD from Cambridge, getting that PhD in 1989. Now, you may be aware of the college system in the UK, where you're not only admitted to an academic department, but also a residential college. And there have been, for many years, colleges that didn't accept women. And in 1988, the last college to accept women was Magdalen College. And in 1988, Sarah became the first female research fellow at Magdalen College, where she really helped transform that college into the welcoming educational space that it is today. She stayed at Cambridge as a lecturer until about 1997, where she made what she calls one of her most important career decisions, and that was to leave Cambridge and go on to the unknown at ETH Zurich, where she was the first female professor in civil engineering, and from what I understand, also the only and first female professor of geotechnics in Western Europe. And so she was really putting her stakes down. And ultimately, she was appointed rector of ETH Zurich in 2015. Now, this shows her tenacity in the technical world, but she also has another side, and that's the athletic world. Sarah is an accomplished and world-class triathlete. You didn't know I could use the internet. Look what I found. She was a member of the British triathlon team. She won multiple European and British triathlon championships between 1984 and 1993. She ran the Hawaiian Ironman triathlon 5 times, coming in 5th in 1985. And this is where my colleague Brady Cox, when he first heard me talk about Sarah, said, she's a badass. And that is so true. She was fortunate enough to participate in the torch relay for the 2012 Olympics in London in recognition for the role she played for bringing the triathlon to the Olympics in the 90s. Now, she started rowing then in the mid-90s, and she holds 3 world records for her age group for indoor rowing. And next year, I think she's moving to the next age group, and she's going to start for doing some more world records there. And her athletic tenacity and technical tenacity intersected at Cambridge, where young PhD students would often ask, why is there a rowing machine in the centrifuge control room? Yes, Sarah would be training while she was doing her geotechnical centrifuge experiments. In terms of leadership, her contribution spans both, again, academics and athletics. At ETH Zurich, she was head of geotechnics, director of the Network for Natural Hazards, joint deputy head in the Department of Civil Engineering, and then, as I said, ultimately rector in 2015, where she had to deal with things like student housing, nursery services, teaching through the pandemic, and just simply modernizing the institution. On the athletic side, she was vice president of the International Triathlon Union, president of the British Triathlon Foundation. I already mentioned she brought the triathlon to the Olympics, but she also initiated a new event, the Triathlon Mixed Team Relay. So it's clear she never has been satisfied with the status quo, and she is always advocating for change. And it was in recognition for the services to engineering and international sports that she received first the Officer of the Order of the British Empire in 1997, so that's the first one. Then you might become Commander of the Order of the British Empire, which she received in 2012, and then ultimately Dame Commander in 2022. Now, I had to show, which one is this from? CBE, okay. But I would be remiss to not mention her technical excellence. So many ways to look at that. She received the British Geotechnical Association Medal in 2013 for this paper on a long-term field study of rainfall-induced landslides, and I think some of the work that she'll talk about tonight will be based on that. Later on in 2022, she was a co-author on this paper that received the Stevenson Medal from the Institution of Civil Engineers, again, working on rainfall-induced landslides. She holds 5 separate honorary doctorates from universities in the UK, Australia, Switzerland, and Belgium. She's been the Cross Canada Lecturer. She's been the Croce Lecturer in Italy. And she's been the other Terzaghi Lecturer in Austria. Now, I know this is a long introduction, but I have just one more slide, because in putting together this nomination for Sarah, I received the most inspiring letter of support from Professor Andy Take at Queen's University in Canada. He describes Sarah as one of his personal and professional heroes, and actually much of the introduction information came from his letter. But I figured I'd just simply read the end of his letter. I reflect that 24 years is a long time since Suzanne Lacasse's Terzaghi Lecture. This implies that there are geotechnical, mid-career women academics who have never seen a woman deliver a Terzaghi Lecture. With the nominee for the lecture of this extreme high caliber, I propose that we must not wait one more year before bestowing one of the most impressive, trailblazing women in our field of geotechnical engineering with the honor of delivering the Karl Terzaghi Lecture. And I say we should not wait one more minute before we hear that lecture. So please join me in welcoming Professor Sarah Springman.
Ellen, I don't know what to say. You're amazing. Thank you so much.
All right, we need pictures.
I'm going to take more. Oh, wow. Thank you so much, Ellen. We've got to do this now. Do we?
Yes.
Which way are we doing this?
Oh,
okay. Oh, over here?
Yes.
Okay, great. Congratulations. Thank you so much. Are you going to take that away again? Okay, thank you very much. Well, thank you so much, Ellen. I didn't realize it was quite going to be like that. But anyway, I'm so grateful, and also to everybody all of the past Terzaghi lectures who said such nice things and who came specially to see me. Thank you, Andrew, and others. It's absolutely wonderful to see you all this evening, and I'm really looking forward to giving the lecture. So, let's get going, shall we? I know there's a clock there, so I've got to keep an eye on that. And it's a real enormous honor to be invited to give this distinguished lecture, named after the father of soil mechanics, Professor Karl von Terzaghi, as he was known in the old days. My very grateful thanks to the ASCE, to the Geo-Institute, and to my very kind nominees. I'm going to consider lessons learned from a series of field monitoring experiments carried out in Switzerland and explore some of the universal themes to explain and categorize responses of slopes to rainfall, the effects of saturation, drainage, and effective stress on mobilized soil strength are discussed together with the role of the depth, permeability, and shape of the bedrock, as well as effects of vegetation. And I hope to offer models ranging from very simple ones to more complex to help understand relevant soil behavior and failure mechanisms to be able to evaluate slope stability. Karl Terzaghi's contributions are absolutely legendary, and his influence in the early days of our international society as its inaugural president were remarkable. He worked, consulted, and traveled widely around the world. And here he is in the year of his mandatory retirement from Harvard at the third international conference in Switzerland on excursion to the 30-mile-long strike-slip fault at the Maloja Pass with the conference chairman, Professor Eugen Meyer-Peter, who was the founder of our institute at ETH and one of my predecessors. So while Professor Terzaghi was renowned for advice on design and construction of embankment dams, these infrastructure slopes with key specifications to retain water rely on principles of effective stress, compaction, a bit of consolidation, of course, too, flow through granular media. And coincidentally, as you heard from Ellen, this accompanied me as a young engineer responsible for quality control at the Monosavu Dam in Fiji in the early 80s. Curiosity through observations of almost axisymmetric stockpiles at the crusher introduced me to thinking about interplay between slope angle, friction, saturation, seepage, direction, and the state of incipient failure in a more natural slope. And this extended later to fascination about the effect of rainfall on natural slopes leading to landslides. So, is this a problem in the United States and even in Louisville? As you can see from this summary USGS map on landslide susceptibility from last year, the answer to the binary question ranges from a resounding yes in almost all states, bar Florida. No comment, including a yes in Kentucky. Vulnerability to landslides may be explored from the excellent USGS map series, which bear closer study. So Quo Vadis, or where next? Well, I'm going to go back now to Switzerland. And from susceptibility to major storm events, here is an example from central Switzerland in summer 2005. Compared to 30-year averages, July 2005 had very little rain, 10 to 30 millimeters less, whereas August was much wetter, 70 millimeters more, as shown by this 48-hour record. Those up to 100 times, so note the many landslides smaller than 1,000 cubic meters marked in brown, and those 100 times larger by volume and more, shown in green circles of increasing sizes. Climate change means that more extreme storms will become ever more likely and frequent in the future. And on this slope, you see small slip failures all over and around the farms. So what influences the initiation of failure? What happens to the slope when it rains? And then where, when, and how much of it will fail? These aspects are important, so let's discuss that. And what's the question, and how will we answer it? I'd like to share what we've learned from field and laboratory tests here, a 38-degree slope, instrumented, in situ shear boxes, large-scale triaxial tests, excuse me, with analytic approaches, equilibrium, physical modeling, and centrifuge modeling, and numerical modeling as well, to aid the prediction of failure to be able to design early warning systems, quantify vulnerability, establish risk, and ultimately protect infrastructure and lives. Excuse me. So what is the status quo? How can we predict from future storm intensities slopes that are going to be unstable? Many researchers summarize the duration of rainfall ranging from 6 minutes to 1,000 hours against the rainfall intensity from 0.1 millimeters per hour to 1 meter per hour for slopes that have failed. The animation shows us basically what's happened. So for probabilistic predictions of rainfall-induced landslides here are also presented with different rainfall duration intensities, completely wet or dry soil, a range of soil depth models, and also with statistically based soil parameters. The authors took factor of safety limiting cases using the infinite slope and determined unconditionally stable regions, conditionally unstable regions, and unconditionally unstable regions in red. And you can see the trends and the variations depending upon the assumptions. I will refer to that later. So my group has conducted multiple field tests around Switzerland. The two main sites I will use to illustrate my points today were each tested over 2 seasons. The first is a granular moraine slope in Gruben, and the second a silty sand forested slope in Rüdlingen. And you can see that Gruben is located in the potentially unstable zones or the conditionally unstable zones in the south, and Rüdlingen in the unconditionally stable and the conditionally unstable zones in the north. And I'm going to mention briefly additional learnings about the influence of bedrock and that of vegetation. 2 important influences here relate to elevation and slope angle. We can see the older Jura mountains running from southwest to north, and the younger Alps in parallel to the south of the Mittelland, which is shown in green. Gruben is located almost 3,000 meters above sea level on slopes at large scale, steeper than 30 degrees, whereas the Rüdlingen slope is relatively low-lying in the Mittelland and with steep local slopes along the River Rhine. So let's put this into context. Here we see data records of recent landslides in Switzerland from 1997 to 2005, plotted as a percentage of, on the y-axis, a number in each group you can see in the legend, against the slope angle on the x-axis. And slope angles vary from steeper than 16 degrees to about 50. One site experienced storms in 2002 and 2005, that's Napf, and trends are similar when you compare red and orange plots. We can observe that slope angles are similar to the typical friction angle for granular soils, whereas some much steeper slopes clearly rely on additional help from vegetation suction and cementation. Some shallower slopes fail too, perhaps through seepage in the slope or soils that are fine-grained with clay. In summary, slope angle relative to the friction angle is important, but it's not the only factor. So let's put this into, let me go back one, sorry, I'm too quick again. Let's do a small digression as a thought experiment in very basic uncoupled soil mechanics. And importantly here, friction is not fiction, whereas cohesion may be. If we have a reliable friction angle mobilized at large strain and shearing at constant volume phi-CV, then the stress state of an element in a slope in a state of incipient failure might plot as shown in black. But guess what? This is not always the case. Stress states are often more critical than this, as shown in red. And it would be steeper than an angle of alpha is equal to phi-CV. So if this slope is stable, then additional strength may be obtained from other sources. For example, if the slope was lightly cemented, then a small cohesion, for example, delta C dash, might be mobilized, increasing the failure envelope, as shown in brown. Should there be reinforcement of soil due to roots, then perhaps there might be a delta C dash R, as shown in green. And finally, suctions could also be enhanced by a simplified determination in which the effective suction can be modeled by a delta C star, as shown in blue. So essentially, we have the equation at the bottom there that could be valid, and as such, a net cohesion could be modeled according to this equation. But it's not very reliable, is it? And it can be a function of strain, bond breakage, saturation. So an alternative model might be to introduce a higher friction angle by an additional value of dilatancy psi. This could be less likely to model cementation, but it might represent the effects of reinforcement and suction. And this dilatancy model is very valid for dense soils as well. This simplified, uncoupled net failure criterion would then be amended as shown and can be used with very simple models to make first assessments. So let's relate this to the state of saturation and flow in a slope. We've seen many examples of dry granular slopes that represent a mobilized angle of friction, phi dashed. If the slope is dry and no water is present, we have case 1, and the angle of a slope in a state of incipient failure is alpha F1 is equal to phi dashed. If, however, saturated flow is passing through the voids, then the slope angle alpha F2 in a state of incipient failure for flow parallel to the slope case 2 is often roughly half of the angle of friction, whereas for horizontal flow at the toe case 3, the slope angle will be flatter. In passing, when the slope is partially saturated, suctions are increasing, the effective stress and the slope angle will be steeper, identified as alpha F4. So this reminded me of Karl Terzaghi's emphasis on simple formulae presented here for factors of safety in an infinite slope. Imagine parallel flow in a fully saturated slope showing streamlines in blue, equipotential in purple, and a standpipe in turquoise will rise from a shear surface at a depth of Z2, parallel to the surface at Z2 cos squared alpha. Now let's review horizontal flow with a standpipe rising to the full height of Z2. Assuming no cohesion and with a phi dash of 35 degrees, one can tell also the pore pressure is going to be lower in the parallel flow case than for the horizontal flow, meaning that effective stress at a slope in a state of incipient failure is alpha F2 19.3 degrees, whereas it's 1.8 degrees flatter for alpha F3. Plotted as a slope with respect to the dry case, we can see the respective slope angles. And should there be a suction of 15 kilopascals, then the partially saturated slope is alpha F4 goes to 45 degrees. And carrying on now with the interface between saturated and unsaturated flow, let's consider how the slope will saturate, leading to a rainfall-induced landslide, through preferential flow perhaps, or through infiltration. Excavating an infiltration test conducted by postdoc Peter Kienzler, the northern site, shows preferential flow through root holes, largely with partially saturated soil around that had not been dyed blue. This leads to the water table building up from the bedrock at depth, and this is called a bottom-up saturation. Should the rainfall infiltrate and then saturate the soil from the top down, then this influences the mobilized volume of debris, which is much less with smaller volumes for the top-down saturation than for the larger ones. And the larger ones also often run out further to more dangerous. We'll see both of these mechanisms in the two field cases. And this affects whether we're also talking about suctions or pore water pressures in the main soil mass as well. So now to the south. The Gruben Glacier, shown on the right-hand side, has retreated markedly, leaving behind a moraine bastion in the forefield with several glacier lakes that collect summer meltwater. These have overtopped the moraines and led to severe debris flows in Sassbarlen village in the 60s before control weirs were constructed. Philippe Tesser was charged by the canton's geologist to investigate slope stability in moraines, and this became his doctoral research project. And here's an elevation of the moraine bastion and the slope in the forefield to the Grubin Glacier. The soil conditions were extremely heterogeneous, but there was a significant fine fraction that retained suctions. And we wanted to link saturation, water flow, slope stability, and debris volumes mobilized due to the rainfall. We instrumented 2 slopes to determine saturation degree, measure suctions and rainfall intensity, amongst other quantities. Water feed flowed from the glacier lake above, and it was a very challenging environment at over almost 3,000 meters above sea level. The test area shown on the 31-degree slope did not fail in either 99 or 2000, whereas a smaller one on a 42-degree slope failed sufficiently. And we investigated the angle of friction on reconstituted specimens in large triaxial tests of a diameter 250 millimeters, maximum particle size 45, conducted to model increasing pore pressure with an anisotropically consolidated constant deviator stress path, and then in situ shear tests on naturally unsaturated soil with friction angles ranging from 39 degrees in the triaxial and 41 degrees in the shear box. And of course, that explains to us exactly why the 31-degree slope was safe and the other not. So let's examine the development of saturation degree in suction with time and how to predict incipient failure. A 1.2 meter long moisture point device installed vertically allows calculation of saturation degree from measurements over sections of 50 to 30 centimeters. Results show that the gradual top-down infiltration almost but not completely saturated in the top 15 centimeters, very little infiltration down to 1 meter below ground level. The rainfall applied is shown at the bottom trace with quite some variability, and then at least 10 millimeters per hour over the week with peaks. One of my colleagues said, "Sarah, what, you want to bring the mountain down?" He was a hydrologist, because it was more than the 1 in 500-year storm. I can't do the Italian accent very well, I apologize. Here we combine data showing above saturation degree, almost reaching 90% at 14 centimeters of depth after 2 days of rainfall in 2000 for the 31-degree slope, and suctions from the tensiometers below installed up to 40 centimeters below ground level. Suctions were 25 to 35 kilopascal before rainfall, and as expected, the shallower devices responded first. Infinite slope stability calculations would show a factor of safety of 10 dropping to 1.5, still safe, with 5 to 10 kilopascals of suction at the end of the rainfall event. But now for the saturation degree in the steeper slope, derived from the TDR instruments, where values of 85 to 98% were reached. The safety factor for an infinite slope was 7 at the beginning, before rainfall, and dropped to 1, obviously, at the point of the failure event, after 2 days of rainfall, with just under 1 meter of rainfall in total. So to summarize, for 1999, taking the moisture point MP and TDR data over 1.2 meters depth, we see reduced saturation with depth, nonetheless increases with rainfall, and the same is replicated across the top 5, half a meter for both years, and for suction in 2000. And as a result, the factor of safety obviously will have dropped. So given the need to quantify shear resistance in situ, we designed, constructed, and instrumented a large-scale portable direct shear box. And how we carved the unsaturated, nominally undisturbed specimens in situ, 25 centimeters square in plan, and placed the box over them are described in papers and in Philippe's thesis. Weights were applied to represent surficial stresses, normal stresses ranging from 13 to 33 kilopascal, and normalizing the shear stress tau mobilized against the large strain shear stress tau u and plotted against dx shows remarkably similar traces for 5 tests for moraine, and when excavated, weighed, and graded post-test, they gave us a saturation degree of approximately 50%. And we wanted to determine shear parameters, obtaining C star to link saturation degree to mobilized shear strength. And here I must mention the valuable collaboration with Christina Yomi as we analyzed large strain mobilized shear stress at failure, tau F, plotted for natural specimens with average saturation degrees of 50% and 70%. 50% saturation, the locus of failure points is linear, indicating phi-CV is 41 degrees and C star 10 kilopascal. The locus for 70% can be drawn parallel to this, but with a lower intercept C star of 2 kilopascal. And then a curve can be fitted to the saturation degree and C star due to suction, taking this data, then two other data points, and assuming C star is 0 for saturated soil, and the relevant equations are prescribed. So combined in simple practical models, by applying this then to the infinite slope conditions for superficial failure, we can determine a critical value of C star at FOS of 1 as a function of unit weight, depth, slope angle, and friction angle. And then what friction angle should we use, having conducted lab and field tests? We find here that our 39% and 39 degrees in the triaxial is also relevant, or should it perhaps be the 41 degrees in the shear box? And we can check then what C star would be mobilized at the depth of failure of 20 centimeters on the 42-degree slope, and input friction angles to see that the C star required is 0.1 and 0.2 kilopascal range, and comparing against the C star SR plot from the shear box data, we obtain the relevant intercept C star for 95% saturation, and bingo, it agrees really quite well. And this is just a very simple model, but actually, in this case, it worked remarkably well. So what did we learn from Grumman? Well, saturation mechanisms after heavy continuous rainfall show very shallow infiltration into moraine, top down, with suctions and factors of safety reduced accordingly, leading to a very superficial slip. But how much of this can we predict? Predictions of the size and extent become feasible with simple models here. Angle of friction and slope angle are relevant. Scale is important, but precisely when will the failure occur? And that's one of the big questions we have to ask and answer. So now to the north. This area along the Rhine near Rüdlingen was susceptible to superficial landslides. 42 occurred in 2002 with net damage of over 1 million Swiss francs. We wanted to explore why and needed a field site that could be instrumented, monitored, and brought to fail safely. Being aware that roots reinforce the ground, we searched for a suitable site, notionally steeper than the friction angle of the ground, but with hints that the slope might fail, indicated here by the downslope creep evidenced through the curved tree trunks. Bedrock was seen outcropping to the top right nearby, and this was part of the TRAM project within the CCS project from the ETH Council. 6 doctoral students and many postdocs worked on the project at many times. The topographical features along the Rhine River Graben indicate slope instability. You just have a look at it, it's obvious. Ground and geophysical investigations were then carried out, including dynamic probing, excavation of test pits, sampling, top of bedrock permeability tests, electrical resistance tomography, and a borehole. Soil depth to the bedrock was found to be variable 1 to 5 meters, with fissures in the horizontally layered bedrock in the underlying marlstone running parallel to the river, and porous layers in the sandstone above. 3 clusters of instruments ringed in yellow were installed, and an artificial rainfall was applied to the site via a hydrant, hoses, and sprinklers. And the bedrock played a really important role with a buttress at the toe and through drainage and exfiltration, all of which affected the slope's response to extreme rainfall. Instrumentation in clusters included devices to measure volumetric water content, suctions, earth and water pressure. We had meteorological and hydraulic measurement systems, and we had steps, lights, and a net to protect the road, and we videoed surface movements and quantified them through photogrammetry. A novel instrument that was through Devrim-AXA, and a novel instrument was designed as a deformation probe as well, and these were then manufactured and installed to measure subsurface movements. The soil mantle was surprisingly uniform colluvium with some clay and gravel. Samples obtained from the test pits were characterized. You can see the accepted Rudlingen soil that we used later on for subsequent testing in the lab, largely led by postdoc Francesca Cassini. And the clay fraction was scanned and found to contain smectite, but didn't have much effect, actually, in the end. Carrying out direct shear box tests in situ in the field, we obtained considerably higher values of shear strength, as shown by the stars, than values determined from remolded specimens in the lab, either with or without suction measurements. And this reflected very low stress levels and presence of suctions and vegetation. In summary, the initial value of phi-CV was determined to be 31 degrees, much less than the slope angle of 38 to 40 degrees. So as you've seen above, surface vegetation was cleared at the site. There were shrubs and trees and grasses. Schwarz quantified root reinforcement then through pull-out and tension tests in the test pits. 1 to 2 millimeter diameter roots tended to pull out, and the 3 to 6 millimeter ones failed. And he constructed a map of the root cohesion on the site, which was delimited by the red dots, the 6 red dots, and we can see many trees shown in brown, bordering the site and in the lower part. So any future instability was expected in the upper part of the field, with a cohesion due to roots of about 1 to 2 kilopascal. Safety on site is essential. Ensuring that access was controlled according to the state in the ground at the test site, I set up a control structure with clear responsibility with internal and external communications based on all on this graph delimiting safety condition indicators. And the cutoff that closed access completely on and immediately around the site was the saturation degree of 75% and higher, or a suction of 7 kilopascals and lower. It worked. All of the doctoral students came home afterwards. That was important. And it would have been my fault if not. An artificial rainfall event was organized with sprinklers distributed evenly down the slope, and double the annual rainfall was delivered over 4 days at an intensity of 10 to 40 millimeters per hour, with minor deformations observed in the top right of the field, but no failure. So given the fissures in the bedrock at the bottom of the field, this was akin to trying to fill up the bath without the plug being in it. And so a second experiment was conducted 6 months later with sprinklers located in greater concentration in the upper part of the field, and roughly double the rainfall intensity at the top led to failure after 15 hours. And we'd learned a great deal from the first experiment, applied this to the second, and I'm now going to show you just a little bit of data. The landslide debris sheared past deeper lateral roots from the shrubs on the right-hand side of the field, which had been cut down to 0.4 meters depth, and some roots broke too, you can see from the picture. Evolution was possible through photogrammetric analysis of the photographs reported by Devrim elsewhere, and the final erosion scar is shown in the upper part of the field on the right-hand side as predicted, following the border on the right-hand side in the shallower soil. And debris was deposited safely in the bottom part of the net, 130 cubic meters. So what did the instruments tell us? Well, the pore pressure was negative at the beginning, with suctions down to 1.5 meters depth. The rainfall coincides with top-down saturation for the first 3 hours or so, but by 6 hours, a water table has built up from a depth of 1.5 meters with a height of 0.8 meter, or 8 kilopascals of pore pressure there. At the same time, the volumetric water content increases and shows probable saturation by 6 hours at the 0.6, 1.2, and 1.5 meter depths. Thereafter, the saturation mechanism seemed to continue bottom up. And I'd wanted to be able to determine the depth to a slip surface during the experiment, and wondered whether instrumenting a strip with strain gauges and calibrating the probe to measure bending and hence lateral deformation might work, and could find a use in the future early warning systems. Armin, now a professor, Ascariniad, was the lead doctoral student for the whole project, and together the team designed, manufactured, and calibrated, installed 4 probes, of which 4 functioned really very well. Deformation probe 4 was installed in the top left of the field to a depth of 2.5 meters. where it was cemented into bedrock, and a time trace of the deduced lateral deformation is given from 4:25 p.m. and continued until failure. We can see the deformation building up with time, and a shallow slip developing at 0.5 meter depth, for a more major one started bulging at 1.2 meters of depth with a sudden acceleration to failure over the last 10 minutes. And while good indications have been given by this instrument, not enough warning would be possible for any to give time to escape, unfortunately. So let's have a look at the, roll it, David, please. This is the first video, which shows the pictures of the landslide every 1.5 minutes. These are the color pictures, and you'll see how quickly the slide develops. You're going to see rainfall, you're going to see lights, you're going to see just typical Swiss slope here, really, isn't it? And it rains and it rains and it rains, and then look at the top right of the field, and you're suddenly going to see a tension crack opening, and all of a sudden, boom, and it's down in the neck. So that's why no doctoral students were allowed to be on the site at that time. Can we roll it again, please, David? This is the black and white version with 0.23 seconds between each photograph. So you can see exactly how the slip develops. So you remember we had a tension crack up at the top, and then it sheared away from the vegetation on the right side, sheared, rotated and sheared a bit, translated, and that was the first 36 seconds. And all of a sudden, here you see it going. Look at the water coming out at the back, the exfiltration, and then it accelerated into the net over the last 12 seconds. Essentially, it became a debris flow at that moment in time. And it reached a maximum speed of about 3 millimeters per second, and detailed vectors were possible from the wonderful photogrammetry, which I haven't, unfortunately, had time to show you today. So here's a sketch describing the interactions, and we can see that it was primarily bottom-up saturation in the upper part of the field, with some minor top-down from the rainfall. We had mainly exfiltration in the upper part, controlled the behavior, with the drainage down in the bottom by the buttress. We could see precursors of movements from a couple of hours before the failure. However, at the end of the day, what worked really well was remediation at the beginning with perhaps deep-rooted vegetation, and by draining the slope, leaky bedrock is especially effective in this case. So I'd now like to move on to some other learnings from physical, analytical, constitutive, and numerical modeling. So I'm going to start with some learnings about the effect of bedrock on the stability of the soil mantle. Armin and our technician team had designed and constructed a climate chamber and a rain simulator to test our hypothesis. After Andy Take, by the way, we learnt from him. And we studied the effect of the bedrock shape and hydrogeological interactions with the overlying mantle of the Rudlingen soil, compacted to 2 meters of prototype depth on a 38-degree slope. Armin developed a new scaling law to model the static liquefaction process in the unsaturated slopes subjected to rainfall mist under increased acceleration conditions of 50 gravities, equivalent to 1.27 millimeters per hour. And photographs taken of the slope showed slope movement and cracks developing at the toe with time. In the top, without any drainage, in the middle, with the buttress, and in the bottom with drainage, showing that the length of, or the resilience, increased from 300 to 600 to 900 hours at failure at the end. So that was very helpful, really. And complementary learnings about the role of bedrock shape and permeability stimulated further physical and numerical experiments modeling a steep scree slope in southern Switzerland, conducted by Daisy Lucas. One concern that emerged was a bedded geological strata that had different depths of cover when exposed to groundwater flow in the scree. during storm events. And the graph shows us the longer the base of the step x2 and the higher the step, the lower the water flow Q required to reach sufficient failure. And that's what it looks like in the numerical models and in the centrifuge. We can see the water forming a spring over the shorter and the longer steps. We can see the very minor scars in the centrifuge, and we can see for the shorter steps and the much longer failure zones over the longer steps in the pictures below. So the message here is be very careful what you wish for. Buttresses might be helpful, and drainage is very good, but exfiltration and saturated flows sometimes bring more of a challenge. So the contribution also of the, I've gone back one, there we go, other learnings from vegetation. What about the vegetation? Well, the contribution of the roots to the shear strength was quantified using a multi-stage direct shear test and in a slope model in the centrifuge by Armin. Simultaneously, roots were planted in the shear box and in the model box using the reconstituted Rüdlingen soil in the same room and tested on the same date. So we didn't have any time effects on the growth of the roots. Surface movements of the vegetated slopes showed faster initial movements, which decelerated as the root reinforcement mechanism was activated. This was also seen in the direct shear results. So what happened was the slope was stable for the entire 1,800 hours at prototype time of the rainfall. So the reinforcement really helped here with a C-R of 2 kilopascals and a phi dash increase by 1 degree to 33.5 degrees. And we had an opportunity to help our colleagues Wei Wu and Barbara Svitala validate a coupled hydromechanical numerical model, which had a multiple hardening evolution of a modified cam clay yield locus for unsaturated soil, which combined root reinforcement and Indra Ratner's sink approach to modeling evapotranspiration. The pre-consolidation P.-C was defined according to increasing volumetric plastic strains, wetting or drying of the soil, and the mechanical root reinforcement. And so this three-stage direct shear test that you can see modeled quite effectively shearing, unloading, reloading, with and without vegetation. So possibly this could be a useful model to incorporate in a finite element program later on. Zooming out to the big picture, and based on another project we joined with the Wald, Schnee und Landschaft group in Switzerland, we tried to quantify the effect of protection forests on slope stability. We can see here the difference between the pasture and the forested patches in the east of Switzerland. And the outcome of advice to cantonal authorities in Switzerland from our project was that forested areas gained at least an extra 5 degrees of slope angle before they were likely to move into a state of incipient failure. And our part in this project was with Dr. Frank Graf, and our doctoral student, Anil Yildiz, was to quantify the effects of the roots on grasses and shrubs, as well as inoculation by mycorrhizae. Graf and colleagues had designed and manufactured a large inclinable direct shear box that could be loaded to appropriate superficial stresses and then sheared to determine mobilized shear resistance and to measure any vertical movements. Essentially, we wanted to try and quantify the additional strength due to the roots and to apportion it either to an additional cohesion or perhaps to dilatancy, C. Yildiz planted multiple germination boxes with diverse plants and grew them for 6 to 12 months before shearing. That was quite an endurance feat, I can tell you. And here are the results showing you the phi-CV of the soil at 34.3 degrees with the plus 5 degree criterion and data showing that peak friction angles mobilized were much higher, especially at low effective stresses. And that, of course, can then be converted into a dilatancy angle of psi max. And these results for relatively immature grasses and shrubs help to explain why steep slopes like those near Rüdlingen remain safe until exposed to extreme rainfall, and this gives confidence also to the cantonal authorities about the plus 5 degree criterion. Moving on to other learnings, starting from novel to simple and increasingly complex and coupled analyses. Just quickly here, a three-dimensional limit equilibrium solution. We sort of looked at it in the terms of a box, and we could add in the effect of suction, also if one wanted as well vegetation, and did some sums. And we can see here that the factor of safety just was 1 with at 1.1 meters of depth, with a saturation degree of 50% and a suction of 3 kilopascals. It's very simplistic, but it's a start, and one can have a look like that. But really, we wanted to move on to slightly more advanced models, and we needed to obtain parameters to describe shear deformation and water retention in soil, which we put into the Barcelona basic model. And so Francesca Cassini carried out these triaxial tests under drained and undrained states, and also model more appropriate stress paths anisotropically consolidated with raised pore pressures. And we use Bishop stress to represent the effective stress. And then to determine water retention properties, Francesca consolidated specimens, 3 different void ratios, exposed to either wetting and drying or just drying cycle in a Fredland cell. The water retention curves were defined according to Van Knuten's equation. The sandy nature of the Rüdlingen soil is clearly reflected in the abrupt increase in degree of saturation at suction levels lower than 10 kilopascal. And then we obtained the parameters for inputting into Barcelona basic model and code Bright. So Ascarini had conducted 2- and 3-dimensional finite element analyses using simulating the rainfall applied in the field as a flux at the soil surface, and he set up the fissures and hence drainage at the base of the bedrock and provided water under pressure to represent exfiltration from the bedrock at the right time. And this was really very effective. You can see the water exfiltration from bedrock fissures proved to be the main trigger, causing increased pore pressures along the soil bedrock interface. And we can see the 3-dimensional version as well, and it enabled us to see the formation and propagation of a failure surface. It's a first approach here, but we needed a more extensive analysis of the triggering of the landslide. So to our more practically focused colleagues, please allow me a few slides to explain briefly the medal-winning work led by Francesca Cassini and Panos Sitoreños, with a more advanced unified state parameter model, or CASM, that has been developed by you. It is YU, not YOU. It is based on a single yield surface that could diverge from the elliptical modified CAM clay, yield locus in gray, with guaranteed normality of plastic strain increments. So this could also incorporate the state parameter T, in itself helpful when considering potential compressive or dilative volume change. The powers N and R constrain the shape of the yield surface, F, on the deviatoric plane, and its emphasis can be changed to either the wet or the dry sides of critical state. This then influences the ratio of the plastic strain increments under volumetric and deviatoric conditions through a non-associated flow rule to the plastic potential G, based on Rowe's dilatancy theory. And finally, the loading collapse curve for each pre-compression state, P0, in a saturated state, can be defined based on Bishop's average skeleton stress, which represents, well, the nonlinear evolution of shear stress with suction. The model was calibrated against Cassini's triaxial tests on Rüdlingen soil at constant water content in both saturated and unsaturated conditions, and the increased shape versatility of the yield locus, and especially an independent control of the intersection of the yield surface with the critical state line, was essential in representing failure accurately and shows quite good agreement. At the time of 14.5 hours after the start of the rainfall experiment, the soil mantle was largely saturated and had been so since after about 10 hours. The pore pressure at the point shown in the lower graph had become positive as saturation was occurring bottom up and the upper part of the slope after about 7 hours, modeling the experimental data in green in terms of time and magnitude really remarkably well. The stress path of an element just above the bedrock is shown from points A to F. Initially, anisotropic consolidation from A to B, 4.5 hours, before shearing at almost constant deviatoric stress, 8.7 hours, reaching the yield surface at C with a P0 of 60 kilopascals, followed by dilation, increasing void ratio, and softening from C through to F at 14.4 hours, as the yield surface shrunk to a P0 of 33 kilopascal, as the stress path reached the critical state line at failure, along with the majority of the soil elements along the failure surface. So finally, the development of the surface displacements at the designated point is plotted against time and measured values, and we can see initial movements occurred after about 10 hours, and the plastic strains increased at the soil bedrock interface, with acceleration at 13 hours and again at around 14.4 hours. And so I think the failure mechanism, you'll agree, has been really quite well modeled. And I think confidence can be engendered by using a validated advanced constitutive model to represent the triggering of a rainfall-induced superficial landslide. However, the critical state models cannot handle tension stresses, and this approach breaks down when mesh integrity has been compromised. So we need other approaches, and we were lucky to work on numerical simulations with Alomir Favero Neto and Ronaldo Boya for a 3D mechanistic model of the flow kinematics using updated Lagrangian continuum particle method, using a smooth particle hydrodynamics, SPH, to capture large deformation, material nonlinearity, and the complex post-failure movement. And two main simulations were done. The second modeled a heterogeneous material with spatially varying cohesion to represent the root reinforcement, and comparing the numerical solutions with the observed failure surfaces and final free surface geometries of the debris deposit, as well as with the observed flow velocity, flow duration, and hotspots of strain concentration, gave us some more insights into the accuracy and robustness of this SPH framework for modeling debris flows. And it was very encouraging, and I think that predicting and mitigating damage from landslides will be ever more important as we face climate change as that continues and worsens, and this must be factored into future work on assets and community protection programs. So folks, that's it, you've survived. What contribution has this research and collaboration made? Well, I think there's been multidisciplinary research and cross-industry research programs have had an impact at national and EU level for assessment and management of risk and links towards policy making. Knowledge has been spread to multiple countries, like today, for example. Valuable collaborations as well were had. I think the technology and knowledge transfer through education, research, and innovation, both with graduating undergraduate and graduate students, through practical engineers engaging with continuing professional education, frequently also through international and national professional societies and institutions, is often underestimated and shouldn't be. It's great you're all still here, everybody, by the way. I'm impressed. In terms of methodology, natural hazard maps at cantonal level have improved estimation of vulnerability, and advice has been offered to design codes and on specific projects as well. And I think we also interacted with expert federal bodies and supranational programs leading into the UN. And so a huge thanks to all of the funding agencies that you can see here. I can't explain them. It's a bit of a logo soup, isn't it? But I thought I should entertain you at the end. And I'd like to just say a closing comment to Professor Terzaghi, visionary in our field. It's a century since his textbook. What an amazing person he is, what he's stimulated. He would be astonished at what we're all doing now. I hope he might be a little proud that his legacy has been so great. But I want to thank all of you for being present and coming in person. Of course, it's all about people. I have to show you some silly pictures there. You can see how much fun we had in Rudlingen. It was absolutely amazing, but on other projects as well. A huge thank you from me to all of the people that I've worked in my group and outside. And picking up on the point that Rudy said, There are many others who will be very grateful that this lecture is now over, particularly Rosie, my wife, and Elspeth, my PA, and a huge shout out also to Gabriella, who was my PA before, and to the technicians who don't often get a mention. They were amazing. Thank you so much, everybody.